Imagine a literal David versus Goliath scenario, but, played out in the world of artificial intelligence. 70%, that is actually how often human evaluators preferred the answers coming from a tiny 1.3 billion parameter AI over a massive 175 billion parameter giant. It literally shouldn't make sense, right? The larger model, GPT-3, had way more data, way more raw capability, but the tiny model won, and it won completely. So how on earth did a model a fraction of the size manage to outsmart its own Goliath so consistently?
Well, welcome to this explainer. Today, we're decoding exactly how that happened by tearing down the 2022 InstructGPT paper by Young and colleagues. Now, this paper didn't just solve a super fascinating puzzle, it established the absolute bedrock of frontier AI alignment. Pretty much every major AI lab today still uses the exact pipeline we're about to explore. It is literally the engine that makes AI actually helpful to us.
Okay, let's dive into this. Here is our teardown map for today. First, the base model problem. Second, stage 1, supervised fine-tuning. Third, stage 2, reward model. Fourth, stage 3, PPO optimization. Fifth, fixing the alignment tax. And finally, why InstructGPT still matters.
Section 1, the base model problem. Why raw models fail. Right, so to understand the fix, we really have to understand the flaw first. And the core flaw of raw language models is that they don't actually answer questions, they just predict text. Take a look at the left side here. You prompt a raw, pre-trained model with something super straightforward, like write a Python function that reverses a list. You expect an answer, right? But look at the right side. Instead of giving you the code, the model might just spit out another prompt, like write a Python function that sorts an array. Why? Well, because pre-trained models are trained on vast amounts of web text. In their world, a prompt is often just part of a long list of questions on a forum. They're simply continuing the pattern they learned. They're playing pattern matching. Which brings us to this absolutely brilliant quote from our source material that just perfectly captures the dilemma. The model is doing its job. The job is wrong. The raw AI isn't broken at all. It's just playing a game of text continuation when we actually want it to play a game of helpful assistance. A massive paradigm shift was needed here. Just throwing more parameters at the problem, making the model bigger, wouldn't change the rules of the game it was playing. So, to change those rules, Young and the team at OpenAI developed a very specific 3-stage pipeline to bridge that massive gap between human intention and machine output. And this is our visual map for the teardown. Stage 1 is SFT, Stage 2 is the reward model, and Stage 3 is PPO optimization. Let's walk through exactly how they tick. Section 2, Stage 1, supervised fine-tuning. Okay, this is the absolutely crucial first step. Supervised fine-tuning, or SFT. In the paper, they collected about 13,000 prompt response pairs. These were literal examples of what a well-intentioned, helpful human would write in response to a prompt. By fine-tuning the raw model on this specific data using standard cross-entropy loss, which is basically just punishing the model mathematically when it guesses the wrong next word, the model learns a new format. It finally learns that it should answer a question rather than just continue a list of questions. But, and this is a big but, here's the catch. SFT alone just isn't enough. It teaches the model the format of an answer, sure, but it totally lacks the necessary signal to tell the model which answer a human actually prefers when you have multiple plausible answers. Section 3, Stage 2, the reward model. So how do we actually teach the AI which answer a human prefers? Well, we use a reward model. Here's how it plays out. The AI generates multiple possible answers to a single prompt. A human labeler looks at them and simply says, hey, I prefer answer A over answer B. Then we train a completely separate, much smaller model, typically around 6 billion parameters, to predict that exact human preference. It uses something called the Bradley-Terry pairwise preference loss. Now, I know that sounds like incredibly heavy math jargon, but it basically just means taking that complex ranking from the human and boiling it down into a simple binary classification that the model can actually learn from. The reward model learns to score these combinations of prompts and responses. However, this stage introduces a pretty massive vulnerability. Notice the size difference here. These reward models are relatively small at 6 billion parameters, basically acting as a flimsy bouncer for the massive 175 billion parameter main model. And because this small model is just a statistical proxy, the main AI can absolutely learn to game it. It starts finding weird, lazy tricks to get a high score without actually providing a genuinely helpful answer. This is what we call reward hacking. Section 4, Stage 3, PPO optimization. That fragile dynamic makes this third stage absolutely critical. This is where the actual reinforcement learning loop happens. Now, what's really interesting about this slide is the KL penalty. In this stage, we use an algorithm called PPO to maximize the reward scores generated by our reward model. But remember, the reward model is highly hackable. So to stop the AI from finding those adversarial loopholes to cheat the score, we introduce the KL penalty. It acts as a vital regulator. Its entire job, literally, is to keep the reinforcement learning policy anchored firmly near the safe, well-behaved SFT policy we created back in stage 1.
To visually understand why this matters so much, look at this comparison. On the left, if we optimize the model against the reward proxy without the KL penalty, the model just drifts into disastrous mode-seeking behavior. It starts spitting out total nonsense strings that the reward model mistakenly scores highly just because it's never seen them before. But on the right, with a properly tuned KL penalty coefficient, represented by that Greek letter beta, the model stays totally grounded. It improves its helpfulness without flying off the rails. It is, for sure, the single most important hyperparameter in this entire process.
Section 5, the alignment tax, fixing regression.
So we have our 3 stages, right? But pushing model alignment this hard introduces a fascinating new complication, the alignment tax. Think of it as a post-RLHF regression. We force the AI to behave nicely and answer instructions beautifully, but in doing so, it actually drops in performance on standard raw knowledge benchmarks like SQuAD or HeliSWAG. We made it a way better assistant, but we accidentally made it slightly worse at basic downstream tasks it just wasn't explicitly rewarded for during that RLHF process. Visually, it looks like this. Human preference, the alignment score, shoots way, way up. Humans love the new model. But the raw benchmark capability dips. The model is basically specialized way too much in being polite and answering prompts, and it's sort of forgotten some of its foundational pre-trained skills. Now, the engineers at OpenAI couldn't just accept that tax. Their mitigation was something called PPO-PTX. The PTX stands for pre-training mix. During that final reinforcement learning stage, they actually mix a fraction of the original pre-training gradients right back into the objective. This simple but honestly brilliant move stops the model from forgetting those downstream tasks, and it was so incredibly effective that PPO-PTX immediately became the gold industry standard for Anthropic, DeepMind, Meta, the whole shebang.
Section 6, lasting legacy, why it matters.
Now, let's step back for a second and look at the massive lasting legacy of this 2022 pipeline. And this brilliantly illustrates why we still study it, the jargon. Pretty much every frontier AI lab uses these exact concepts, but they often mask them in, industry slang. This slide right here is your decoder ring. When people say instruction tuning, they mean stage 1, SFT. When they talk about the RM, they mean stage 2, our scalar regressor trained on human preference. The regularizer is our KL penalty holding the whole system together. And the RLHF regression is just that alignment tax we just discussed. The exact mechanics we just broke down are the underlying reality of all these buzzwords. So the crucial point is this. Alignment is an entirely different access from capability. Remember our hook from the beginning? The 175 billion parameter base model had vastly more raw capability, far more knowledge. But the tiny 1.3 billion parameter model won out 70% of the time. Because it had superior alignment, it knew how to present what it knew. However, it's definitely worth remembering that the capability floor is still set by the base model. You literally can't align a model into knowing facts it never saw during its pre-training. Furthermore, you absolutely cannot understand modern AI critiques, alternative architectures, or safety exploits without first having this exact 3-stage InstructGPT pipeline mapped out in your head. When researchers worry about reward hacking, they're attacking stage 2. When they propose new methods like DPO, they're basically trying to collapse stages 2 and 3 into one step. When they talk about sycophancy, where an AI just tells you whatever you want to hear, they're pointing out that human labelers themselves are a fundamentally biased signal. Which leads us straight to the bleeding edge of AI research today. The InstructGPT pipeline works incredibly well to make models helpful, but it completely relies on a fragile proxy of human preference. So I want to leave you with this provocative thought to chew on as AI continues to scale up. What happens when the AI gets so incredibly smart that it learns to trick the reward model completely, perfectly gaming our preferences without actually doing work? It is absolutely the ultimate question for the future of AI safety. Thanks so much for joining me on this explainer, and definitely keep questioning what's going on beneath the surface.